And I will ask you hear the sound? And I fill up. Why? When I empty the bottle and we hear lower pitch but getting higher pitch by hitting the bottom. Why? Okay, maybe students will say, hey, professor, you are really you are teasing us because those are the questions appropriate to middle high school students, but still it's a good question to the graduate students. And I ask you to explain those phenomena using the concept I will explain to you. And another acoustically small space. You see, the alcohol level of this one is higher than this one, and the frequency of this one is higher than this one. So it makes sense, right? 128 hertz. Okay, another demonstration. Okay, it's too high. Okay, you hear it? Low frequency one, and this one, very high, short. So that indicates that certainly the length of pipe has to do something with the frequency. Okay. Okay, now let's start this one. What is really happening when I blow this? Okay. Suppose I have a vessel that has a volume V, and this one has a length L, and the area is A. And when I excite it, what happens is, let's call this as a pressure at the outside of the neck, and this is the pressure inside of the neck. And what I can see here, when I blow this, the change of pressure at the inside over here, with respect to time, will be proportional to change of volume with respect to time, but should be minus. Because if the pressure is increased within unit time, then the volume has to be shrinked, decreased. And I want to change this proportionality to equality. To convert proportionality to equality, I need some constant that we call proportional constant. And that has to be something, but that should be what? The dimension of that should be pressure, volume. In other words, how much volume change I will get for unit pressure change. Okay? That we call compliance. You may be very familiar with the pressure over volume. That means how much pressure change I would get for unit change in volume. Okay? This is 1 over compliance. Okay, now notice that I have an equation that relating P in and V, and I want to have an equation that only has one dependent variable. For example, P, only P. I want to have an equation that only handles with P in. Okay. That motivated us to think about our famous 3 physical parameters that describes every physics in acoustics. What is it? What would be? The 3 physical parameters. What would be? Think about what we learned in chapter 2. Huh? Huh? Mass damping? Okay. What dominates acoustic wave propagation? Huh? What dominates acoustic wave propagation? I was asking you what would be 3 physical parameters that governs acoustic wave propagation. Pressure? Pressure? Are you sure? And? Don't you remember this famous picture? What would be? Density and velocity. What is the relation between this and this? Euler. What would be the relation between this and this? Conservation of mass. What determines between this and this? Huh? Okay, final examination will cover from chapter 1 to chapter 5. Okay? Because that is a final examination. What determines between P and rho? Huh? Huh? Constitutive relation. That means dP d rho for isentropic process is C squared. Okay? These relations are really the fundamental relation that we must remember. If you take a course from me, then you must remember at least that one. Alright? Everybody?